Good morning. My name is Linderman. You know, as I sit down at my computer and I use things like large language models, which have been a topic of conversation here, I'm intrigued at how pushing the boundaries of computation affect how we do things that have traditionally been the domain of human intellect. And what we're here to talk, the panelists here to talk about today, is really how we are pushing the boundaries of computation and how computation is pushing the boundaries of the aerospace industry, both today and into the future. I come from the Air Force Research Laboratory. I'm the chief scientist of the Information Directorate, background electrical engineering, computer science, and high performance computing. And so I've been really interested in how these technologies are advancing. So today I've asked the panel to consider 5 different ways that we're pushing the boundary. First is pushing the boundaries of computation itself. Neuromorphic computing. I've lost my microphone, there we go. And basically, how can we think about computation fundamentally differently than we have in the past? The second is where we do that computation. Whether it's in the cloud or on the edge, how is this enabling new classes of applications, perhaps in the context of autonomy? The third is changes how we apply this technology. For example, how can some of these new models of computation be combined with more classical CFD, finite element analysis, computational electromagnetics, things that this industry cares about, to do that fundamentally differently. The fourth is, touching on what are some of the things that need to happen in order for us to get there, to really achieve some of the visions that we're talking about. And then finally, what does this community need to do? And a lot of that's in terms of how do we develop the workforce? What are the skill sets that need to come together? How do we have to have new interdisciplinary teams and other things in order to really make this a reality? So with that, I'd like to turn it over to the panel. We're going to go from your left to right, and each of the speakers, starting with Bill, will briefly introduce themselves and give a little bit of their perspective, touching on one or more of the themes that I brought up. There's an application then, I guess, for submitting questions. And so my main job will be keeping track of those. So please contribute questions, upvote those questions. And after we've made one round through the panel, we will start the Q&A session. Bill.
All right. Thanks very much, Mark. Good morning, everyone. It's great to see you all. I'm delighted to be speaking with you about the boundaries of computing. My name is Bill Casebeer. I direct an artificial intelligence and machine learning laboratory for Riverside Research, which is a 730-person not-for-profit research and development center focused on Department of Defense and intelligence community needs. So my team really has 3 principal technical focus areas that push the bounds of computing. First, we develop, using methods like deep learning and all the buzz phrases you're familiar with, algorithms that find things in stuff. So we look for objects and activities in a variety of types of data sets, because especially in the intelligence community, we're concerned about setting up tripwires that tell us when certain types of activities are taking place. So in order to do that, we have a line of research that uses large language models as assistive agents to help intelligence analysts tap the variety of programs they need to use in order to be able to find things in stuff quickly. So that, I would imagine, will be one dimension of the bound of computing that we'll talk about today, is how things like large language models are enabling us, our analysts, to do things that wouldn't even have physically or temporally been possible for an analyst to do 5 years ago. The second focus area my team has is that we look at using neuromorphic computing to make our algorithms faster and more size, weight, and power efficient. So neuromorphic computing is just a catchphrase that talks about non-von Neumann architecture computing. So computing substrates that don't have a centralized processing unit, but instead are much more biologically realistic insofar as they are networks of nodes that look like neurons you might find in the human brain. And so in much the same way that the human brain has some fascinating capacities, think of all the compute power that our 10 to the 14th neurons and the 10 to the 15th power connections up here do for us with only 30 watts of power, so do neuromorphic substrates have some of those same capabilities. So we've done work, for instance, for a couple of sponsors where we build algorithms that find things in stuff using unusual data sets and unusual types of sensors. In one case, an event-based imaging sensor, a silicon retina, if you will, that is just a change detector. And so the thought there is, well, if we're gonna have compute that uses a silicon retina, why not have the compute be neuromorphic, since our brains process the information that come from our retinas? And moreover, the retina itself, just a fun biological fact, is actually nothing but the tail end of a cluster of millions of neurons, right? So your retina really is part and parcel of your brain. And when we did that, when we built those algorithms and tried those out on a neuromorphic computational architecture, we saw significant size, weight, and power savings, and were able to do things like find single pixel simulated hypersonic vehicles in overhead look-down imagery. Finally, third, so that's, I think, another boundary of computing that we'll talk about today. Third, my team looks at how we put both of those kinds of algorithms together with people to make a change in how work gets done. So that's a human-machine synergy team. I have about 10 researchers who look at those topics. And the only thing I'll point out there is that right now, most of our algorithms are blind, deaf, and dumb relative to the activity of the users that are using them. That's too bad, because we know that effective teams don't work without coordination. And so one thing that we want to do inside of our lab is to use things like theory of mind modeling, which is the capacity we all have to make sense of each other's mental states, to engage in larger cognitive state estimation projects. We want to give our algorithmic friends and teammates the eyes and ears they need to know when I, as a warfighter, am cognitively overburdened, so that maybe they can take a task off my plate and distribute it to an algorithm. So that's a third boundary of computing that I hope that we'll talk about today, more efficient and effective ways of generating human-machine synergy via cognitive state estimation in human-machine teams. And with that, I'll turn things over to Givi.
All right, good morning. My name is Peyman Givi, and I'm with the University of Pittsburgh, and also a member of the Pittsburgh Quantum Institute. I have been working in the business of computational fluid dynamics, turbulence, and combustion for the past 40 years. And I have had the opportunity to work at academia, in a private industry, and also in the government laboratories. So the areas that I'm going to touch upon on this, on pushing the boundaries of computing, the first one is a subject of quantum computing. And this evening, I will be giving the whole lecture on it. And what this thing is, quantum computing is a lot closer to aerospace application than we think. And I will be showing that. I've written review articles on it that show how that aerospace community can be using those. So that's the topic from technical aspects that I will be pushing for. The second area that I really would like to talk about, I took the first CFD course that ever offered back in the 80s. And during this time, I've seen how this whole subject has been developed. The whole aerospace calculations has been developed. And one of the things that I really think that in order to move forward, we need to do two serious changes in our educational program. One of them is that to train the students across the disciplines. And that's a lot more serious than before, especially if you want to go to quantum or you want to do anything else. You have to cross the boundaries, and those subjects has to be taught at the graduate and undergraduate level. The second is the field of computation is very different from the way that we did computation 20 years ago. 20 years ago, first you are fluid dynamicist, and then you use a computer to do things. Now, it is a lot more emphasis on people who can do the actual programming. So in that way, a lot of our students, a lot of our workforce, postdocs, are very much trained in interpreted computing. And I'm noticing it in academia that, the number of people who are interested or doing algorithmic development or compiled algorithm, compiled programming is very, very small. So as we have a large number of people who can do computation with interpreted languages, they become very handicapped when they want to use these other ways of compiled programming. And that becomes very important now that we have a lot of use of the GPUs. And as in some areas, we are moving toward TPUs. In those things, compiled programming is also very important. And along those lines, I do like to have some suggestions for a lot of our government agencies in the way that they would want to fund computational experts. As we have right now, I know that DOE has a program, very competitive, in which the students are trained in the high-performance computing. And the fact is, if you are in any area of the aerospace that you want to do computational with today's standard, you have to be heavily trained. So those are the only areas that I think I can contribute to. Thank you.
I'm Greenwald, and I'm a program officer at the Air Force Office of Scientific Research. So AFOSR is the Air Force and Space Force's basic research funding arm, and we look for high-risk, high-impact research, basic research that will ultimately benefit the Air Force, Space Force, and Department of Defense missions. So I manage two portfolios. One is cognitive and computational neuroscience. And that program has two main focus areas. One is on the mechanisms of perception, cognition, and behavior. And the other part is at the intersection of neuroscience and artificial intelligence. And my goal is to have a virtuous cycle between the two so that predictions from one part of the program can be tested in the other. And I'll return to the neuroscience part in a moment. The other program that I manage is computational cognition and machine intelligence. And that's an AI program that's looking at aspects of machine intelligence, reasoning, inference, autonomy, planning, and also the machine side of human-machine teaming. One thing that I think is interesting about the program, though, is that it specifically excludes statistical and deep learning approaches as a focus, and focuses on other parts of AI where many of the big players currently aren't focused. But turning back to the neuroscience, I think that there's a lot that we can learn and use from principles from brain research and neurobiology that we can apply to the brain. And one of my big questions over much of my career has been what sorts of novel computations that can brain-inspired software and hardware allow. So beyond some of the energy efficiencies have been very important, especially for power-constrained platforms that you'd find in air and space, and are certainly an interest of this group. But going beyond that, what are the novel capabilities that you might achieve? And if you look at neurobiology, you may find some surprising things or interesting things that you could build into hardware and software. For instance, a grant that recently finished from Sarah Marzin at Claremont McKenna College and Joost Lefeber at University of Groningen, Netherlands, was looking at cells in culture. And so these cells in a dish were given electrical stimulation, but using temporal patterns that had correlations in them. And what the researchers found was that just naturally, these cell cultures in a dish, not doing anything else, started trying to predict when the next pulse would come. And they started synchronizing their firing with the anticipated and predicted stimulation. So what was interesting about that was that this idea that prediction is really seems to be a fundamental mechanism of what neurons do and potentially a fundamental aspect of intelligence. Another grant that recently got started from Sam Gershman at Harvard is looking at paramecia and single-celled organisms. Now, when we think about the brain and about learning, and even as the basis of artificial neural networks, the core element is the synapse. It's this connection between cells, and we know that the strength of those connections varies as a function of learning and determine the probability with which a downstream neuron will activate in response to its upstream neighbor, firing an action potential. But paramecia are single-celled organisms. So they don't have synapses, because there's only one cell, but they still learn. And there's been evidence that they can learn, for instance, what simple stimuli like vibration will indicate to them, and they can retain that memory for at least 24 hours. So they have some aspect, at least, of long-term memory, and yet no synapses. So what are the computational properties of that allow the single-cell organisms to learn? And so that's kind of the goal of this research, to look at how they're learning and what the computational properties are, and then how potentially those might be integrated down into artificial neural networks. So there is, in addition to the normal things that we think about in the human brain, in particular with being able to learn from few examples and being able to transition what we know, transfer from one task to another, we have very robust cognitive capabilities, and those are the types of things that we'd like to have in machine intelligence systems. And so that's kind of where the space is that I've been working in, looking at relationships between neurobiology and brain-inspired hardware and software. Thank you.
Thank you. And thank you, Mark, for having me on the panel. It's very exciting to be here with such an august group. And I feel like this is last but least over here. My name is Shawn Weil. I'm a principal cognitive scientist at Aptima. The way I typically describe Aptima is with a virtual Venn diagram, that on the one hand, we do social, cognitive, neuroscience, behavioral science, and on the other side, we do different. We have people who have different backgrounds in computational science, in aeronautics engineering, in artificial intelligence. And then I talk about what that intersection is. And that intersection has a lot of really interesting and wicked hard problems in performance assessment and in training and in interface design and in human-computer interaction. But thinking about pushing the boundaries of computing, I think what's going to happen is that intersection is going to get larger and larger and larger as those two circles in my Venn diagram really start overlapping with each other. On the human side, you start thinking about brain-computer interfaces. The old information processing metaphor used for human cognition, that's been out the window for a decade or more. And now we have much more nuanced understanding on how the brain is actually doing computation. On the other hand, on the computational side, we have increasingly powerful quantum computing approaches. You've got neuromorphic computing that my colleagues were talking about. And when you start putting all of those things together, you start seeing that the two, the human and the computer, are getting closer to each other in a very real sense. So today, what does that mean? That means that the kind of distributed computing, the edge computing, the federated learning that we are seeing, and the human-machine, first teaming and interaction, then symbiosis, those things are converging in a very real and powerful way. Today, there are more naturalistic ways in which individuals and groups are interacting with ever more powerful computational systems. And we tend to think of those as still separable. But as we move forward, we have to start thinking of the basic unit of computation to be the interaction and aggregation of the human components and the non-human components of complex systems. And that's going to impact the domains of AIAA in fundamental ways, from the training of new engineers to the design of new systems to the actual control of air and spacecraft themselves in ways that we couldn't have imagined 10 years ago.
Okay, well, thank you very much, Shawn and everyone else. So bring in questions. We have one so far. Bill, since you and I both mentioned large language models and GPT, I think you've earned the first question, which is, in the current environment, how do we effectively distinguish between truly novel capabilities and hype or marketing?
Yeah, great question. I'm sure everybody in the audience is familiar with the hype curve from Silicon Valley, right? Where a technology is initially, its possibilities are trumpeted, and then when those possibilities aren't immediately realized, you enter this trough of disillusion. And then there are several years before you finally start to have the technology settle down enough in such a way that you can actually reap its performance potential. And so I think LLMs, large language models, are just on the lee side of the curve, that hype curve that people talk about in the Valley. And what I mean by that is that I see a lot of promise with LLMs. That promise is writ large in both the incredible things that you can do with them and that you see in the headlines daily. I dare say that 5 years ago, if you had mentioned to someone that there is a technology that will be able to pass the Turing test, such as it is, that you probably would have been laughed at, and yet now you and I can experiment via the ChatGPT Open API, a system that passes the Turing test presently, from what I can tell. So the obvious promise of these technologies is there. Now, on the other hand, we know that there are lots of technical hurdles that we have to overcome before we can leverage these agents to actually get work done. Those are also in the headlines. So those include things like understanding the causes and consequences of hallucinations in large language models, understanding the relationship between formal specification of problems and the computational activity that takes place in the guts of these large language models, so that you can get something like a performance guarantee or some provable computational bounds out of the LLM for your particular problem set. And finally, I think we need to understand the relationship between the implicit models and explicit models that exist inside these LLMs. So, one of the things that's going on in the hidden layers of these networks is that because of the statistical regularities they are detecting in the language input that they ingest from these large corpora, I believe that the LLMs are generating lots of implicit models of the world. And yet our toolkits that we use to explore those implicit models, to characterize them, to understand how they interact to produce the behavior of the large language model, honestly are relatively poor. And so I would love to see improvements in those toolkits so that we can better characterize those implicit models. And I think that will connect back to those first two areas as well, that when we do that, we'll start to understand their bounds and get some performance guarantees out of them. And we'll probably also start to understand then how we retrain those LLMs so that we eliminate hallucinations and constrain the way the models are used for compute. So that's my first stack at it, but I'm sure our other members have things to say.
So if I can add to that, two points. The first is that there are going to be emergent properties of these generative AI products that we don't understand yet. And there are going to be people who dismiss some of those, maybe they're even hallucinations, but those emergent activities as spurious, when really that is giving us hints into what that implicit organization is. That insight can carry us a long way. But the second thing, going back to the original question about where is it on the hype curve, I've thought about this a lot, and one of the things that I think distinguishes the current revolution in generative AI is that it's already commoditized. You know, a lot of times you see products on the curve and there's one company that has it, or there's 3 companies that have been developing VR goggles or what have you. Generative AI is everywhere. Everybody has it. And that means that there's going to be testing and validation at levels that are 10, 100-fold what some of the other technologies on the hype curve are. So I think very quickly we're going to be able to tell signal from noise in terms of where it is applicable and where it really falls short.
That's great. You know, actually, it's actually a decent segue into the second question was, you mentioned the human-machine teaming. How do we train the human to be maximally effective in this new regime?
Yeah, I mean, there's a whole burgeoning industry of prompt engineering. And in a very meta sense, there are LLM models that are designing the kinds of prompts that people are going to need to interact with the system. That kind of naturalistic interaction with these models, I think, will increasingly become the norm in which people are interacting with complex systems. And that has pluses and minuses because you lose a certain amount of control and specificity when you don't have the direct control of the dial. On the other hand, you'll be able to convey ideas and expectations for outcome without having to know the guts of the system. I think it will fundamentally change the way in which people are doing their work, from one where their primary role is creator to one where their role is editor and validator. But that will probably vary from industry to industry and use case to use case. I can't wait to see how not just my kids who are 13 and 16, but the children who are being born today, how they change the way that they talk about people who are digital natives. These are going to be natives of a whole new sort.
Okay, thank you. A couple questions on quantum. And one is, you know, is there a relationship between AI, ML, and quantum? And what does that look like? And then another question is, how do you see quantum transforming the aerospace industry potentially?
Yeah, good question.
And don't use all your best lines from tonight.
Well, you have to come for tonight's lecture to see the full text. You know, when we started working on this business of quantum computing, and you know, people said that this thing never happens, not within our lifetime or whatever. And you know, I'm really pleased to be surprised to say that, you know, we are a lot closer than we originally thought. There are several ways by which quantum computing can affect the aerospace industries, and it already is doing it. There are ways by which that we have, and these are the terms that I invented some years ago, and it is becoming very routine now, especially in the physics community. People are using them. One of them is the quantum ready. Right now, we have a whole bunch of algorithms that come from, their origin is from quantum, and they can be used for actual computations in aerospace. I have used some of them, for example, in large eddy simulations, Monte Carlo method, turbulent reacting flows. So those are those algorithms that are already developed, except it takes for us, the aerospace scientists or engineers, to be familiar with them and find the ways of using them. And the number of them are growing, especially now people in physics, in condensed matter physics, they see this thing now they are moving toward aerospace calculations. Now, the second way that is most recent, and we called it quantum inspired, and that's a methodology now which is becoming very popular, especially again in the physics community and plasmas. And those are the algorithms in which they're rooted in quantum, but they have classical implementation. you can use them classically for the problems that we are solving right now. I will show you tonight that you will see that some of these algorithms that the Hilbert space that, for example, you use for computational fluid dynamic, the actual amount of space that you need is a lot smaller than what you're actually doing with the most sophisticated CFD calculations. And those are is going to have immediate impact in our calculations. Now, the last part, that was the first part of the question, the relationship between quantum and artificial intelligence, they're highly coupled. There is a large number of quantum algorithms right now that are used especially for optimization problems. The field of machine learning by quantum computing for artificial intelligence. You will see the number of books that are just being published this past year. Because of the connection of the two of them with a lot of variation of quantum algorithms and the kind of optimization problem that they use in machine learning.
Great, thank you. Hal, I have a question that might be down your line. Applying lessons from biology, what analog to dopamine could be involved in anticipating next actions and establishing coherence of action?
Sure. The role of neurotransmitters is well documented in the brain. And there have been various attempts along the way to implement that in computer algorithms. I can think of one there was an IARPA program a few years ago that had the neuromodulatory systems as a big basis for kind of these larger computing models based on that were supposed to investigate cognitive bias. Along with other aspects of how the brain computes, this is one thing. You've got chemicals that flow throughout the brain that modulate behavior. You could probably use similar strategies in algorithms or hardware, depending on what you're trying to do. But in general, when you look at the brain does what it does because it's a biological system, and we are, in quotes, computing with lipids and other types of biological material that we don't necessarily need to replicate in artificial systems. Spiking neural networks are a big part of that. We still don't really understand what the necessity is computationally of spikes. Are they really efficient when you're computing with fat, or do they have other computational properties that are just really important to incorporate into our artificial systems? So I think in general, the brain provides a kind of like what I think about is when I was learning to roller skate as a kid, there was a bar that I could hold on to at the rink, and as I was learning to skate. And when I was ready and more confident, that I could move away from the bar. But basically, the brain gives us a good starting point, and until we have when we have good reasons to deviate from that, then go ahead. But otherwise, replicating a lot of the functions and structures may be helpful in advancing things that we're doing on the artificial side.
Thank you. So I kind of touched on this earlier as a question, and it came up again. What do you see as the biggest impact coming to the aerospace industry through these new forms of computation? And what do we need to do for our students to prepare them for that transformation? And I'll let that open to anyone who'd like to take a stab.
Yeah, I could jump in and kick us off. Yeah, great question, Mark. So I think in general, the revolution that we're seeing in machine learning and artificial intelligence in the last 10 years with the success of large language models, the advances we made in deep learning and other methods to kind of rapidly adapt a system to its environment. For the aerospace industry, they're going to open up all kinds of new avenues for human-machine synergy inside the industry. Those can range from different ways from pilots of vehicles to interact with the vehicle on up to different ways to engineer command and control systems that have lots of complicated parts doing various functions. I think AI and ML has the potential to revolutionize kind of both ends of that spectrum. And I'm sure my fellow panelists are going to kind of amplify those points. I would say bigger picture, For those who are starting their careers, who are seeking a career that combines aerospace issues with AI and ML, that you also have a secondary expertise that you combine with your principal expertise in computer science. So, on my team, we're always looking to hire the mythical unicorn-like full-stack developer who can, work in everything ranging from databases on through to a fielded application that improves performance for a customer. But what we also look for is somebody who can step past the command line and understand how developments in biology, or how developments in social systems, or how developments in political science impact the way we use AI and ML. So that would be the big picture message I have for those of you at the start of your careers. Focus on your depth in computer science. You can exercise your muscles in artificial intelligence and machine learning, but don't neglect your intellectual curiosity in the second area. Because one of the first questions I would ask you before you join my lab would be, awesome full stack development capabilities, but what else are you interested in that might offer us a new way to think about how we apply compute in those aerospace areas? So what's your computer science and story that you want to tell as you look for work in this sector?
Peyman.
For the past 10 years or so, our department have been trying to hire people who do artificial intelligence, machine learning, deep learning, like everybody else. One of the things I have noticed with a large number of people who are coming for giving discussions, giving the presentations on the application of AI and machine learning in their areas, one thing was very obvious, that their fundamental knowledge of the subject is really poor. And we have a large number of our own students that are taking a whole bunch of these courses in machine learning, artificial intelligence, and they know how to run these programs. Thanks to Google and a lot of programs and TensorFlow, whatever, that they can run and they can get very good answers. But I have been really surprised at the number of people who just don't understand the fundamentals of it. So last year I proposed to offer a course on mathematics of machine learning. And it's just basically talking about some of the concepts of probability, optimizations, linear algebra, and combine them all with some sort of a programming, either Python or Julia. And one of the things I emphasize in this, using the Python or Julia or MATLAB for that matter, is the end part. You have to be able to be doing those parts yourself to see what is it that you are optimizing. Because machine learning and all of this is nothing but just a sophisticated statistical learning. So you have to know the fundamentals of statistics. If you don't know Bayesian statistics, using them to use a machine learning package that happens to a large number of courses or subject matters that I've seen is not going to be helping you. So I think in those areas, the fundamental responsibility comes to the universities to be teaching this them at very early stages. And the same thing would go. I mean, now that you are going to see, we are going to be shifting toward quantum, to be teaching those things at the very earlier stages, maybe at the senior level, at the graduate, undergraduate, or first-year graduate students.
Yep. Shawn.
So I agree completely with the idea of taking a multidisciplinary approach as fundamental to being able to pull methods, concepts, theories from one place and see how they fit in another place. I also agree that you have to understand the fundamentals of the computational approaches that you're using, because if not, you're going to be basing your work on assumptions that you can't be confident in. But I'd also say that there was a time that in order to be a successful engineer, you had to be really good with those punch cards that we saw at the plenary session this morning, and with a slide rule. And that's not the case anymore. There are different skills and different things that you need today in order to effectively do the work of aeronautical engineering. I would also say, and this was something that was really difficult for me as a graduate student and is difficult for new staff members that I work with, who have spent their careers pushing the boundaries of science very incrementally. You get tunnel vision where you are, And it's very difficult then to move from the ground level to the 30,000-foot view and back down again. I would urge you to figure out ways in order to contextualize the work that you're doing, to understand how it fits in with a larger set of research and development, and understand how it contributes to the kind of impact that the field is trying to make. And if you're able to do that, it gives you additional motivation for pushing the boundaries of science.
One of the questions that kind of relates a little bit to the maybe the hype question is we hear a lot about, you know, the true north and neuromorphic computing and quantum computing, and we hear a lot less about top 500 exascale type traditional high performance computing. Is that just an artifact of the hype, or is there something fundamentally going on that suggests that, you know, maybe traditional HPC has peaked in terms of relevance, and these other things are really seriously catching up?
So, right, I think the advances in high-performance computing have enabled a lot of what we're seeing in terms of the generative AI networks. We've got much faster computing capabilities. We have storage has become much less expensive. We have these capabilities for computing, but the fundamental frameworks haven't really changed in really, I hate to say it, but decades. The computers that we have are basically the same exact architectures. And so they're bigger, they're faster, and even with deep learning, it's still the same neural networks,
right,
just on larger, more capable computers. So how do we get past that? And it's easy to say, hard to do. We really need new ideas and new theories that will push us beyond the paradigms that we have now. Doesn't mean we throw them away. They're going to be absolutely useful going forward. But how do we enhance that and add to it so that we have computing capabilities that enable new approaches and new algorithms in effective ways, both in terms of power and time and the other important resources?
Okay, thank you. We received a question, maybe this is best for Shawn and Bill. There's a question on, you know, obviously the amount of money that goes into creating some of these models is tremendous, tens of millions of dollars. How does small businesses compete, or how does it either enhance or inhibit their ability to compete in the marketplace?
Well, I think that, again, like I said before, a lot of these things are commoditized, which means that there are small businesses may not be able to develop models that are domain specific on their own, but they'll be able to partner with companies that have the economies of scale to develop those models and partner pretty effectively. I mean, small businesses don't do cloud computing at scale. You work with Amazon or Oracle or Microsoft or Google in order to get that capability. It's just something that you buy by the hour or by the gigabyte. I suspect the differentiator instead is not going to be access to those models or even the development of those models, but the application of those models in ways that meet the needs of whoever the customer is, whoever the user is. And as it relates to aviation and aeronautics, you're going to see that those custom models are going to be critical in the laboratory environment in order to do some of the fundamental engineering of new vehicles and new approaches, and are going to have some applicability even for the implementation and the actual flight of some of these vehicles. So I don't see that as a major impediment, because I think there's going to be an economy that's built around exactly that problem.
And to complement Shawn's point, I fully agree that compute power is a commodity. and that because a lot of these technologies are being open source, that businesses of all sizes will be able to leverage them to get things done. So I see a future where, as we kind of work together to build our airplane, that we might pull it up to, our Amazon fuel station and plug in some cloud compute. We might have a small business that builds a particular kind of display or interface that's in the cockpit of the airplane using their exquisite expertise. And we might have traditional integrators, right, who bring all of these niche technologies and the commodities together in a way that actually produces a new capability. And that traditionally has been the model of our blue sky research and development agencies inside the Department of Defense. So if you think about your typical DARPA program, for instance, the Defense Advanced Research Projects Agency generally doesn't fund a single sole performer for any program, right? They fund teams, and it's because that rich ecology consists of the provisioners of the commodities, of the systems integrators, and of the exquisite knowledge that you get out of small businesses that are going to be needed to build that next airplane or space vehicle.
Okay, thank you. Peyman, you mentioned trying to have courses that actually teach the mathematics underlying this. We've done some similar work with that. It's kind of hard in the sense that there are a lot of fun parts of AI, and then there's the hard work of understanding the underlying statistics, probabilities, and all of the frameworks that go to that. But one of the things that certainly ChatGPT has shown is that now we have lots of people that have very little technical background using these classes of technology. And there are certainly risks associated with that. And how do we create, there's goodness in that applicability is much broader. There is risk, of course, that people don't understand what they don't understand. And these are so heinously complex that they won't understand the underlying models. But how can we prepare people to use these tools appropriately without making them PhDs in statistics?
Yeah, this is a fantastic question. And this is not only in artificial intelligence or machine learning. In CFD, we have been experiencing it for years now. There are a large number of industries that are using these packages, computational fluid dynamic packages, and running them for special applications. And in many of the cases, they are getting very, very wrong results. Those computer codes have been developed not to blow up. I mean, that's one of the things in CFD we teach the students. When the code is blowing up, that's a good news, because it's telling you there is something wrong. If it doesn't blow up, then you have to worry about if you are doing it correctly. So those codes, that's how they are. And in CFD, that has been the business for many years, and it's still going on. A large number of my students who graduated in this business have gone to these companies like ANSYS, CFDRC, that are developing those codes. They see that there is very good codes if you know how to use them, if you know the basics of it. And if you really don't know the basics of it, if you don't know about the discretization schemes, you do not know what is the method that are solving those differential equations, you trying to simulate a gas turbine, but the fluid inside there is not anything else but jello, because you just change the viscosity of it by a large factor, so in order for the thing to be stable. The same thing is happening. The same thing is happening right now in AI and ML. We have a large number of engineers that they have used these machines because it's very easy to use. I mean, if you have any experience with any of TensorFlow or PyTorch, they're relatively easy to use. But the answer that you are going to get is really the optimized answer the way you want it. So the way that we are trying to do, at least in our university we are trying to do, when we develop these basic courses, we heavily advertise them in industry. Especially with the local industry we have, and we ask them, we send them the brochure that say, look, you are using these techniques, you're using this CFD code, or you're using this AI code. These are the fundamental courses that if you want to learn. And I really don't see any other way of doing it except that, encouraging people to come and take these courses or interact with us. Now, our message has been really nicely received because now we have some of the even government agencies, like we have in Pittsburgh, NNL, very close to us, and they're sending their engineers, their scientists to collaborate with us. So they learn and they be trained in those businesses. And I really don't think there is no other way of teaching them by just means of just teaching them by education.
Shawn, you were looking over this way.
Yeah, well, I was thinking about the car metaphor, right? I don't know how the internal combustion engine works. Sorry, I'm not an engineer, which is embarrassing maybe, but it doesn't stop me from driving a car. And my mechanic might know how the engine works. You kind of hope that he does, but he couldn't design one himself, right? So in a larger ecosystem like this, there have to be people who understand each of the elements at an atomic level. But those people are not necessarily the ones who are going to be spending their time doing the application of it. They might be terrible drivers in this metaphor. So I think we have to understand how much fundamental understanding the user needs in order to detect bias, in order to detect the hallucinations or the subtle problems, without requiring that they have that PhD in statistics. On the other hand, you have to make sure the people who are doing the design up front understand what those applications are likely to be in order to make sure that what the fundamental models are going to meet those objectives. And it's always going to be a give and take. It's always going to be a dynamic system in terms of what people know and how you cross-train them. And I think this is good advice for some of the emerging engineers to understand that same level of understanding going up and down and going laterally in their expertise.
Do you think it's going to be like driving a car, though, where, you give them a few rules of the road, you have the terrifying experience of driving with your 16-year-old kid, but over time, people learn the norms and expectations and start to detect, dangerous situations? Or do you think people will have a very difficult time converging on those norms and expectations just through the repetitive use of these technologies?
So since we're overextending an analogy, which is an occupational hazard and a bad habit of mine, I can think of two things here. First of all, when you're talking about the road, those norms, they weren't really emergent, right? The rules of the road were codified, and they were codified because they weren't emergent. The infrastructure was not there. People did not know they had to stay on one side of the road versus another in the 1920s. And so we had to create those rules so people could do that work within those parameters. Not a perfect analogy because hopefully our versions of generative AI are not crashing into each other, causing a lot of deaths. But maybe some of these applications, especially in aviation, they are life critical like that. But the second thing is, talking to my late father about him learning to drive. He was born in 1942. His first car was a stick shift. It did not have power steering. It did not have power windows. It did not have a mirror on the right-hand side. It was a different vehicle than the ones that my children are going to learn on, which have safety features and have sensors all over the place. Which means, so to overextend the analogy, the version of ChatGPT that we're driving now is not the same one that we're going to be driving 5 years from now. The technology and the people using the technology are going to be adapting with each other. And so you would like to think that some of those parameters are going to be emergent and just in terms of market need, and some might in fact be codified where people try to design within the lines.
To jump on Shawn's bandwagon, and your bandwagon too, Mark, There's a sense in which these artificial intelligence and machine learning driven systems are just another tool, right? They're no different from a monkey wrench that you might use to solve a plumbing problem that you have in your house. And so you don't necessarily need to understand every dimension of the monkey wrench, right? It's metallurgy. Maybe there are metallurgists who can do that. But you do need to have some general idea of its design specification, its performance parameters, so that you don't, over-tighten a joint and wind up ruining your sink. So there's the sense in which AI and ML systems are just like monkey wrenches. However, there is another sense in which AI and ML-driven systems are very different from monkey wrenches. Generally, monkey wrenches don't talk back, right? So AI and ML systems, insofar as they do exhibit some dimensions of autonomy, are agents. And probably one skill set we need to bring to bear to understand their limits is to know how to interrogate those agents so that you can understand their skills, capabilities, and performance bounds. In just the same way that you would if you were coaching a Little League baseball team. You would ask your 14-year-old pitcher, how does that fastball feel for you? Why don't you try a curveball instead? You would coach them. And I anticipate that some of our systems that are complicated in this way of the future, we're gonna have to think of ourselves as coaches managing a team, and that does require a broadening of our skill set beyond more traditional physical engineering of putting together the monkey wrench, I think.
I feel like we've spent a lot of time talking about AI. I just want to focus on a couple other areas for a second. So I'll start with Hal, and then I'll come to you, Peyman. I'm going to ask you a quantum question. So I'll preface that I'm not asking you a quantum question. What do you think is the most intriguing or interesting revolutionary change in the way we think of computation that's coming out of the kind of the portfolio that you're leading, or other areas that are associated with it? Well, you mentioned, for example, the paramecium work. It's pretty intriguing. Single cell things learning. I have no idea what. But are there fundamentally? So obviously things like machine learning is come a long way, and quantum computing. We've been thinking of those algorithms at least going back 20, 25 years. Are there new things on the horizon that are fundamentally different than those two that we should be keeping an eye out for?
Yeah, it's an interesting question. So on one hand, what we've seen is the kind of the commoditization of computing, where there's just more capabilities available.
Right.
But in terms of new directions, certainly quantum, and I'll let you address that, is one where it seems like it's closer than some of the other technologies. In terms of brain-inspired computation, I think that we're still understanding so much about how the brain works and what it's doing. We know the brain it's not a computer. It's a nice metaphor that we've got. But maybe there's strategies there that will inform novel things. But it's really a big question mark for me. It's I've been really passionate about neuromorphic computing since I first got interested in that as I was finishing up my graduate school time, and I really don't yet know what the novel computations would be, because we think about our computers as general computers that can compute everything, but maybe the representations that the brain uses that make those even more efficient for certain types of problems.
Well, for instance, we traditionally our computers give numerically precise answers. But, we talk about modeling probability and statistics but with fairly precise mathematics, although we can talk about squeezing the bit representation, but not fundamentally stochastic computing. Is that an area that of course, quantum computing has a
Has a large
has a large part of
Yeah.
stochastic.
But you're reminding me too of the analog computing approaches, where it's not exact, it's not precise out to many, many digits. It's more approximate. And you're trading off that approximation, and what you're gaining is lower power consumption. And maybe there are other ways of optimizing what we do where we're able to trade off different aspects of the computation so that they use less power or just converge more quickly.
So, Peyman, on quantum, I just want to raise it up a little bit, because a lot of people in this industry probably aren't following it. What kinds of things does quantum computing do well, or do we think it's going to do well on, and how is that different than traditional computing?
In aerospace, we are experiencing all the consequences of the two revolutions that we are in. The second quantum revolution and a big data revolution. The amount of data that are being generated is just, as they are saying, it is doubling every year. Every 12 months, the amount of data that we have to work with is doubling. And how to process them, how to analyze them, and that's, parallel is exactly what this high performance computing has to deal with. So dealing with those data in this revolving way of analyzing them and using them for our modeling, it requires a specific training on understanding the physics of the problem with the data. The data is using to enhance our physics, and our physics is going to help us to get more data, the coupling of the physics and the data together. So that's one area that is going to be big for a long time to come, and artificial intelligence as a part of it. Now, with the second quantum revolution, in which quantum computing is a part of it, we are now learning, this is different from the first revolution in quantum. At that time was the quantum science. Now we are learning to use the quantum science and use it in the form of quantum technology, to use it for the things that we need to work with. Now, in the business of what exactly right now quantum computing is going to do for aerospace, well, it is doing applications already in a lot of chemistry calculations. Has a lot of applications, optimization in machine learning also. Area of quantum materials, of machine learning, quantum computing have been very useful to it. These are the areas that right now it is making an impact. Some of the other areas that is going to be making an impact within the next couple of years is the new paradigm of computations. Well, tonight I'm going to be talking about the method called the tensor networking and matrix product states. And those are the things that you are going to see it in the next 4 or 5 years is going to come very heavily into the aerospace calculations. The new generation of students have to learn how to be doing those calculations, coming away from the general areas of what we do now, spectral, finite, spectral element, or whatever methodologies, and moving into the areas in which we can shrink the domain of our computations. And so with these two revolutions are ongoing, and we are going to see the consequence of it within, as we go on, within the next 5 years or so, you are going to see a major marriage of quantum and machine learning together, and what a major effect is going to have in our business.
Okay, Nick, do you have something to add to your, or how you're just looking at me like, no, didn't know. One of the fourth theme that I brought up earlier was, what do we need to do to get there? What kind of investments, maybe on a national level or pick your level of granularity, do we need to be making, in terms of test beds, infrastructure, seemingly power distribution networks for some of these things? Are there investments that we need to be making to either push the bounds of computation or its application to the aerospace industry? Anyone's?
So one of my colleagues, Brett Perkinas, is a program officer at AIAA and leads a program on the science of test and evaluation. So he's got good insights into this. But one of the things that we've talked about and that I've been interested in for several years was how we test and verify and validate these AI systems, where they're constantly evolving, and unlike the wrench, they're changing size and shape and growing new aspects to them. So what you test today is not necessarily the same system that you're going to test in a short period of time. And that seems to be a very important hole to fill. So when I was looking into this a few years ago, I was talking with the FAA, and I talked with the Army, and because these are groups that are looking at various types of platforms where they're looking at incorporating AI into ground-based or air-based platforms. And it seems like nobody really had a good handle on that. This was a few years ago. Maybe things have changed within the past 2-3 years. But this is something really that we need to solve, because we need to be able to trust the systems that we deploy are still going to work within the bounds that are intended.
Okay. Peyman.
I really think the United States needs to take a serious look at this issue. In the area of computations, the way that we do things as a university professors that, writing for proposal, getting funded, it is extremely difficult to train the students in computations when our funding is in something else. So when I'm doing something in turbulent combustion, this is on the physics of flames and turbulence and other aerospace problems. But at the same time, the computations that we are doing is extremely sophisticated. And it is really the funding that we get from those areas to train the students in high-performance computing and the leading edge is extremely difficult. I strongly feel that in the government, our agencies, DODs, DOEs, NSF, they must allocate a lot more into the training of our students in computational science and engineering. The amount of funding for that particular thing is very small. And what we do in the domain areas is insufficient to be funding those. That's very important. The second thing that is also as important, I really think that there should be a mechanism to encourage the interaction of universities with industry, especially in aerospace. In aerospace, the industries are very conservative. They're taking them a long time to get familiar with the new ideas, new methods. Some of the turbulence models I see that they're using in aerospace belongs about 30 years ago. Those methods, they're just adjusting the constant. They just don't want to know about the new methods that are being developed. So there should be a mechanism to encourage this kind of interactions like the way they do it in Europe. To make sure that these people are interacting, and it has two major benefits. One is that our students, when they graduate, they can go to this industry and make an impact, not to go backwards, not to go back and say, okay, forget what you learned, go back what we did 20 years ago. And the second thing is that we have a very, a strong influence of industry in the government panels. So they would be, advising the governments that, these are the areas they should be funded. The same thing would go. The same thing is true for government laboratories. When I started as my career as an assistant professor, I really, enjoyed going to NASA Langley, NASA Grant, to working with those people. And, those kind of programs back in the, early 90s were very much encouraged. I don't see that anymore. Or at least, I don't see the extent that it used to be. So encouraging of that industrial interaction and with the government and universities and government laboratories and universities is one of the areas that the country should take it very seriously.
Okay, thank you, Bill.
So I think we need two major investments in order to kind of realize the advantages of expanding computational boundaries. One, and this is to foot stomp Hal's point, I think we need better human-machine teaming test beds. So in our lab, we use VR digital twins to do some of that initial testing, but I think we could triple down there and actually expand the number of test beds that are available to industry that let us put our algorithms and computational systems into contact with the warfighter earlier on. And that will support the classic V of systems engineering, where you validate requirements and then verify that your full system actually meets them. So that's one area of investment, more human-machine teaming test beds that incorporate artificial intelligence, machine learning, and novel forms of computation at the edge into them. Second, I do think we also need to double down on that cognitive state estimation approach that I mentioned earlier. Because as we go about producing these tools that are more than just monkey wrenches, we don't want to have them operate in splendid isolation, right? You want your baseball team to be aware of what the coach is saying, to understand it, to understand what's going on inside the coach's mind. And I think we need almost a Manhattan-style approach to cognitive state estimation for aerospace autonomous systems that help us fully understand what's going on in the pilot, the UAV controller, the air component commander's mind as they interact with the systems that our industry produces. One quick note also is that I know we have a very diverse audience here, but you were asking earlier about novel forms of computation, and all three of our panelists had great things to say there. It's sometimes good if we're from disciplines to share some pieces of writing that we found inspiring in that area. And so I would just call out to any more kind of classic aerospace engineers in the audience, David Marr's book called Vision. The first chapter of that, he has a really great explanation. It's cognitive science-y about the relationship between hardware implementation levels, algorithms, and computation. And if you read that first chapter of David Marr's book, Vision, that will ground you to think about a lot of the advances that you were gesturing at, Mark, with your question. Second, one of the pioneers in natural computation is Dana Ballard, and Ballard has a series of books that I found inspiring in my career. One is called Natural Computation. So it talks about the types of computation that occur in nature at multiple levels of hardware implementation, to refer to Marr now, and at multiple timescales. So read the first two chapters of Ballard's book, Natural Computation. And if you really dig that, follow up with the first two chapters of his book, Brain Computation as Hierarchical Abstract Representation. And that'll really get you started in thinking about how these novel approaches could generate new capabilities for the DoD.
Well, you know, when I look at especially some of the generative AI models, and, you know, speaking of reading lists, Conrad Wolfram's book on the maths fix talks about the 4 stages of problem solving, you know, defining the problem, reducing it to a computable form, doing the computation, and then assessing whether the computation answered the original question. Yep. And that our education system focuses on step 3, which is what computers are ideally set to do versus those other 3 steps, which are almost entirely in the human domain. And using these generative systems, you realize, A, how important the input is, the prompt, if you will, if I'm thinking GPT, but also, how do you assess at the end that this is an accurate and legitimate answer to the question? And for all of these technologies, that can be a challenge. You know, did I get the right answer and do I trust it? And how do we develop kind of that cognitive skill set to not trust, but verify, if I were going to quote a former president, these techniques. So that would be on my reading list. Any other reading list suggestions for the audience? Okay, we got a couple.
Marr was a good one, and one of the first books that I read when I was starting graduate school.
Excellent. We're rounding around into the kind of the conclusion here. I wanted to spend, one of the questions that came from the group was, what is the most exciting thing you see coming around the corner? That, let's see if I can actually find that. Yes, what new technology are you most excited about becoming more mainstream in the next decade? And we'll check back in 10 years, you know, see how you did. Why don't we start on that end, Shawn?
Sure. You know, I started out talking a bit about the convergence of the neural and the computational. And I do believe that our knowledge of the similarities and differences and the ability to more directly integrate human computation with some kind of distributing computing capability, those lines are going to get more and more blurred, starting with naturalistic interaction with the generative AI systems of various sorts, not just ChatGPT, but using gestural controlled, using drawing images, all sorts of things, and moving from that to brain-computer interfaces that are interfacing directly with this high-performance, non-von Neumann architectures. And it is the stuff of science fiction, but so many things that were the stuff of science fiction are now in our pockets. So I'm very excited about seeing what new ideas, what new designs, what new innovation and capability that convergence brings us.
Okay, Hal?
So I'm passionate about the neuroscience, and one of the things that, when I started my portfolio, my neuroscience portfolio 5 years ago, I started with the question, how do neurons communicate and represent information? It's the holy grail of neuroscience, and certainly it's a very tough problem. If someone solves it, they probably get a Nobel Prize. But it seemed like a really good starting point for my portfolio, and I'm doing what I can to kind of push that. It's very difficult. But when I'm coming across projects that are helping to push that along, I try to support that. Where I see that is if we're able to understand that, on the neuroscience side, it's going to certainly advance research and advance applications, whether it's prosthetic devices or human-machine interfaces. But it may also translate into how we build our AI networks and our computing networks. So I think there's a lot of promise there, which will then trickle into things like neuromorphic computing, which is also benefiting from other technologies now. You're seeing more advances in both the material side, but also photonic computing. So it's a lot of things coming together that I think will ultimately give us benefits and new ideas and new capabilities down the road.
Do you see an acceleration? What's the second derivative here? Is the pace of the neuroscience in our understanding accelerating, or is it just kind of pacing along? And do you think in the next decade we'll see some fairly significant advancements?
I certainly hope so. I think that the pace is accelerating. We've got better tools. And I think that's making a big difference because we're able to collect larger data sets from more of the brain. We're able to do things less invasively in many cases. And there are new techniques that we've got, like optogenetics, that allow us to manipulate things at a very low level. So we're able to, and even a grant that I've got at UC Berkeley, where they're stimulating individual photoreceptors, which is something that's never been possible before, because if you shine a light on the retina, it's going to activate various types of cone photoreceptors. They're able to target individuals. So we're looking at various types of systems at very low levels, which will then give us insights. But I think overall what we're learning about the brain is that there's still so much more, and the more we learn, the more complex it is. At the same time, the science is advancing, and I'm looking forward to seeing what happens in the next 10, 20 years and beyond.
Okay, Peyman.
The most exciting thing I see what's happening now is the merging of the quantum and classical world. I think now we are at a stage that, it is very exciting to see a lot of condensed matter physics and people in classical engineering, they're talking and working together. It's just natural to think that, many of the classical problems that we work with are dealing with complex systems. This field of condensed matter physics, they're dealing with many body problems. I mean, you want to use the Schrödinger equation for many, many bodies is a very complex thing. Well, in engineering, we are doing it all the time, except that we have never been able in the past to combine the two together. And this is where right now it is happening, that the merger of these two communities in dealing with classical problems, and I think aerospace is going to benefit substantially from it.
Bill?
Three fantastic answers. I like all of those. So I think Peyman, Hal, and Shawn all identify really fascinating growth areas. If I had to pick one, I would say that in the next 10 years, I am super excited about the potential of using the novel forms of computation we've mentioned to build artificial, moral, and ethical reasoners. And what I mean by that is I think it's now within our grasp to build an artificial conscience, a system that can serve as an advisor to people working in the aerospace domain about what actions are permissible, what actions ought to be taken, what actions ought never to be done, all in the context of using the types of technologies we develop for things like warfare. And so I know that places like ONR, DARPA, and IARPA have had some interest in this area of building an artificial conscience, and I anticipate that in the next couple of years we'll see some significant investments from DARPA. and helping us realize the applications of things like large language models to reasoning comprehensively in the moral and ethical domain. So if that's of interest to you, one framework I would recommend, because we can sometimes get a little bit fuzzy when we think about ethical, legal, and social implications of our technologies, is something called the 3 C's framework. And that's the idea that really most moral and ethical judgments can be boiled down to questions of character, consent, and consequence, the 3 C's. Character, what virtues or vices do we need to exhibit as people so that we flourish as human beings? Aristotle and Plato are your exemplars here. You may remember them from college. Consent, that's the idea that human rights are really important and that we're all agents and that before you involve me in your project, you ought to get my consent to be involved in that project. That actually underpins the rules and laws of war that guide things like the way the Air Force thinks about whom they can make a legitimate target during warfare. And finally, consequences. Good old utilitarianism, John Stuart Mill and others, who remind us that one of the most important dimensions of our actions, morally speaking, is whether or not it produces a greater amount of happiness for the greatest number of sentient creatures on this earth, humans and animals alike. So I think that machine learning and artificial intelligence, novel forms of computation, can help us make better judgments about character, consent, and consequence. And one example of that we have that's real and live and has been implemented, we can know to one of our sponsors for the conference, Lockheed Martin. So Lockheed has implemented something called the ground collision avoidance system in some of their airframes. So there are F-16 drivers and others who are alive on the Earth today because an autonomous system made the judgment that they were about to drive their airplane into the ground, intervened, took over the flight controls of the airplane, returned it to straight and level flight, and then put the human pilot back in charge. And so those extraordinary circumstances where we have human-machine synergy helping do something that is morally and ethically praiseworthy, like saving the life of a pilot who is otherwise task-saturated or fixated on, say, a bombing run, very common thing you can see in terminal phases of mission accomplishment. That, I think, is a live example of an artificial conscience in action. And we need to grow that paradigm across all 3 of those C's using the technologies our panel members have been talking about. That project has me super excited for the next decade.
Well, that's fantastic. One of the things that interests me is, to the extent that I'm allowed to speak as a moderator, is, we talk about exploration and exploitation as you're learning new things. I'm excited about how generative techniques will allow us to more rapidly explore corners of the design space that before were perhaps impractical or just too time-consuming to do, but you couple that with things like we can now 3D manufacture fuselages for small aircraft. Okay, couple these things together and show how we can do very unusual or unpredictable things in order to maybe satisfy new mission sets or maybe have more affordable systems or more tailored systems to specific things. I'm excited to see how the envelope of designs that we can consider can expand through the use of these tools. We're coming down to the end of the session. I think I got through most of the questions. We spent a little more time on AI than I would have predicted, but it was a great conversation. It's exciting to see the new computational methods, and we talked about quantum a lot. We talked about the neurocomputing. We didn't get down to the details of memristors and other things. We did touch a little bit on analog computing, so maybe we got halfway there. We didn't talk too much about edge computing, but how we implement autonomy, how we do that ethically. You touched at that at the end. I think it's going to be very exciting. Clearly, the application domains, the application of computing to the aerospace industry, I think we hit on that a lot, which I think is hopefully one of the key areas of interest. And finally, we touched a little bit on, how do we educate? How do we, not just new students, but how do we bring people in industry up to date? And a lot of that is that partnership with academia that maybe we need to broaden or certainly think seriously about to create the workforce with the competencies in whether it's statistics or whether it is in physics, but creating that interdisciplinary team that we need. With that, I'd like to thank my panelists. Thank you very much.
Thank you.
Thank you for having us.